Tonight, we're going to turn this building into a giant games console using a few of these and a lot of imagination. Welcome to the Christmas Lectures. To be hacking some amazing things tonight. But I'm going to show you something very simple to start with, just to get you into the hacking frame of mind. I'm going to start with a little bit of graffiti. Now, all the mobile phones we have these days, they're so advanced that they've actually got 100,000 times more memory than the computer that was used on the lunar landing. And do you know which bit I'm going to use first? The light. I'm going to show you something that maybe you didn't know about a fire exit sign. Did you know you could do that on a fire exit sign? It's cool, isn't it? You can write on the white bits. Now, it fades quickly, but I think that's probably actually quite good. The material is absorbing the light there, so it doesn't emit it straight away. Now, there's two reasons I wanted to do that. First, just to show you that here is my fire exit. And second, just by understanding how everyday objects work, we can manipulate them. We can play with them. I'm Danielle George, and I'm a Professor of Engineering at the University of Manchester. And I want to show you that anything is possible with a little bit of tinkering and a little bit of imagination. So if I just peel off the green part of my fire exit sign, and instead of using my phone, I want to print a message using my homemade wand. But I don't want to do this. I want somebody else to do this for me. So here we have a tablet, and we should be able to send this information to my LED wand. So, how about you? What's your name?
Sasha.
Sasha. Hi, Sasha. Right, what I want you to do, Sasha, is just write a very short word, just first short word that comes into your mind, okay? And then press send. I don't want to know what it is, but Dave, the cameraman here, is going to show everybody else. But you just tell me once you've actually done the word. Are we done, Sasha? Yeah? Brilliant. Okay, so what's happening with this is if I press this down, Sasha's word should be sent. The LEDs are flashing, so Sasha's word should be sent there already. So if I now go over my photoluminescent paper, I should be able to print out Sasha's word. And here we have it. Sweet. Brilliant. Checking out your word, Sasha? Yeah? Brilliant. Okay, now that was just a bit of fun, but that's just what the heart of these lectures are all about. I want to be using some simple electronics, simple components that we all have around our house, and combining them with some coding, with some software, to do something really exciting. Now, the building blocks of technology are all around us and in our grasp. And the great thing is, you don't need a laboratory. You can start to address many of the engineering grand challenges that we have just by tinkering at home. Your garage, your bedroom, your kitchen table is your laboratory. In these lectures, I'm going to be taking three everyday components that we take for granted every day: the light bulb, the telephone, and the motor, and showing not only how they work, but what problems we can solve with them. So let's get started with the light bulb. Now, as a girl from Newcastle, I'm very pleased to say that this was invented by a Geordie, by Joseph Swan in 1879. And I want to honour this great invention that we take for granted every day by setting ourselves a grand challenge. Let's do something amazing with the light bulb that Swan could never even have imagined in 1879. Now, who likes to play computer games? Oh, lots. Good. You're going to love this lecture. So, drum roll, please. Sounds great. Tonight, we are going to turn a London skyscraper into a giant games console. This is the Shell Centre at London South Bank, and our aim is to turn all of the windows into a giant computer screen and play a Tetris-style game on this. Now, this actually makes me quite nervous. So I want to know how nervous it makes you feel. How confident are you we can do this? So by clapping, I want to know how confident you are. Can we do this? So, can we do this? Wow, okay. Pretty good. Excellent, well. I tell you, you're a lot more confident than I am at the moment because I know how many steps we've got to go to do that. But I love your confidence. But before we break that down, I need some help playing this game. I need someone to get ready and go out to that building to be able to control our skyscraper. We've got a taxi waiting outside, and I need someone to jump in there right now and link up live with us from the Shell Centre. Now, you won't get to see the rest of the lecture, I'm afraid, but you would be part of something amazing. You are going to be part of Christmas lecture history. So, hands up. Who would like to go now? Okay, you down there. Yeah, brilliant. Okay, give them a round of applause. Okay, what's your name?
Harrison.
Harrison. Okay, Harrison, and you have a parent or... Okay, is that your mum there?
It's teacher.
Teacher? Okay, right, Harrison. Okay, teacher, are you okay to go with Harrison? Yeah, is that okay? Brilliant. Okay, so what's going to happen is you're going to go with Judy. We're going to put you in a taxi, which is waiting for you and your teacher now, okay? And then we're going to link up live with you at the Shell Centre, and you get to play the game.
All right.
All right? Brilliant. Thank you very much, Harrison. Okay, whilst Harrison is on his way to the South Bank, we need to think about the steps we need to take our crazy idea to actually playing a game on the skyscraper. And we need to do it in less than an hour. Now, I'm an engineer, and when I'm faced with problems that I think are just too big to solve, I like to break that problem down into steps that I think I can solve. So, let's break it down. First, we need to turn the building into a screen. Then, we need to be able to code that game. So we need some software as well. Then third, we need to make a controller, some sort of gamepad, in order to play that game. Then we'll be going live to Harrison at the Shell Centre to play that game. And hopefully, he'll be there in that taxi that was waiting for him, so he'll be waiting for us. So we've got less than an hour to do all that. Okay, right, let's get started with step one. Now, the key to this is finding a way to turn that building into a giant screen. And we can put anything on screens. We could put on my screen here a lovely image of the Shell Centre, or images of giraffes. Or we could even put the photographs that were taken of you guys this evening. Brilliant. Oh, that's a good, excellent. Are you recognizing yourselves? Excellent. Some of you look very happy to be here. That's good. And it doesn't matter how far away those screens actually are, or how big or how small those screens are. They're all controlled by the internet. And that includes the big screens. You know the big screens that you see when you're out maybe shopping in Piccadilly Circus? like this big screen out near Piccadilly Circus. We could control that from right here. And that's exactly what we're doing right now. Look at where your photographs are, Piccadilly Circus. This is a live picture.
In the building.
It's brilliant. So the people on this bus will be looking at your faces at Piccadilly Circus. I think you're going to be cheering up a lot of shoppers this evening. They look brilliant. So you're famous. You're out there already on a giant screen. But I think we need to understand how screens like this one work. So if our cameraman was to zoom in even further onto these screens, we'd see something that looked a little bit like this. We'd have hundreds of LEDs, or light-emitting diodes, all arranged in a grid. So on this screen, we have 32 by 32 pixels, or picture elements. And I should be able to display anything on this screen. So I should be able to just show you some information that I have already on my laptop. Or I could just show you what's in my picture gallery, or what's on my desktop. And you can see all of these LEDs are reacting to what I'm doing on the laptop. So if our aim is to turn our skyscraper into a giant screen, I think working out how our small screen works is a pretty sensible first step. But how do you turn a light bulb on if you have a grid of lights? Well, if we zoom in even further and take just a 4x4 section of our grid, we can just see the basic elements, which are really just some light bulbs. Then we'd need a mechanism of making them turn on and off. Now, I could just build a switch for every light bulb I have, and that's okay for this because I'd only need 16. But for my screen here, I'd need 32 by 32, which is 1,024 switches. And for the Piccadilly screen that we've just seen, wow, I'd need hundreds of thousands of switches. So it's not very efficient. So I think we need to understand how screens actually display an image. So I need a volunteer to come and help me do this. So yes, you down here. Okay. What's your name? Charlie. Okay, Charlie. We stand here. Okay. Now, Charlie, we've got a light here that's already switched on. Okay. If we wanted, say, to light this bulb, what do you think we'd have to do? Have you got any idea?
Make a switch for that bulb.
Yeah, so we've got these two things here. What do you think we could do?
Well, they've got a little dial on them, so move it.
Yeah, go on, try moving that one then. Brilliant. And if I do the same with this one, it moves it across there. Excellent. So we've managed to go from here to here. Good. And if we want to go back to there, what would we have to do?
Move that one again.
Move this one again. So all we've done is just given this switch a different message. So, and the clever thing about this is, Charlie's only had to use 2 switches to do this. And this is how small screens work, and actually much larger screens. The computer breaks down our picture into pixels and tells our switches which lights to light up. But Charlie, I think we've got a bit of a problem here, because we can turn one light on, but how do we turn all the lights on at the same time? How do you think we could do that? Can we do it with this?
I'm not sure if we could do it with this.
What about if you move that really, really fast? Would that work?
Well, yeah. Well,
try it, yeah? Should we try it? We like just trying things. So you try that one.
Okay.
Yeah, and I'll try this one. Now you see, well, we're definitely moving it. We're definitely switching that light. And maybe if you switched fast enough, we might see an image. But I don't think you and I are going to be able to switch fast enough here, are we?
No.
So I think I'm going to need something else to help me. I think I'm going to need a bicycle to help me explain this. But thank you very much, Charlie. You were an excellent computer. Now, what Charlie and I were just talking about there, about switching the lights very, very fast, is a phenomenon that is commonly called persistence of vision, or flicker fusion. And I'm going to use this bike to help me explain. Now, you can see this bike is slightly different. The back wheel has been hacked here. And basically, the owner has turned the back wheel into a screen. So what we have are a bunch of our LEDs, our light-emitting diodes down here. And then we have a little microcontroller, so a little computer in here. And then we also just have a little bit of software that's already been preloaded. And we have 3 of these strips on our back wheel. Now, I know what you're thinking. Surely that's not enough to form a screen, is it? We want to be able to see an image. So if I spin this wheel slowly, I can see I'm having some sort of input. I am affecting that. I don't know about you guys in the front there, but I'm not seeing an image yet. Are you? No? I don't think I'm going quite fast enough. So I think we need to go a little bit faster. Now, I'm not going to get on this bike, but Andy, my friend, is. So hi, Andy. Get yourself on there. The Royal Institution's very own answer to Bradley Wiggins is going to ride for us and see if we can see an image. So nice and fast, Andy.
Okay, yeah.
Brilliant. Now, can we see something? I can see something from here. It says Christmas lectures. Can we see it? Yeah? Brilliant. So what's happening there is all of the pixels are not lit up at the same time, but they flash so quickly. Oh, brill, there's a light bulb as well, yeah. That we're getting that perception of continuous light. So it looks like all of them are lit up at the same time. That's brilliant. Thank you very much, Andy. By turning on the lights in turn, we've managed to create that illusion of a static image. And this is exactly how LED screens work. From the very small screens that we have here to the very large screens. Screens like on top of the BT Tower, for example, which we've also taken over tonight. This is great. We're taking over all the screens in London. Now, it looks like all of the lights are on here to display our wonderful Christmas messages. But actually, only some of them are on. But we're creating this perception of continuous light. But can we apply what we've just learned here to our skyscraper? I've still got that question. How do you turn a whole building into a screen? Well, thankfully, we chose well with our building. So you can see our building is very rectangular. So it has windows which are like pixels, so our picture elements. And we have 13 floors and 14 windows on each floor. So 13 times 14 is 182. We all knew that, of course we did. And all the parents knew it, I'm sure. So we have 182 pixels. And like our small screen here, we need lots of lights. But we also need ways of controlling those lights, of turning them on and off. Now, the Shell building already has lots of lights in them, but they're all controlled floor by floor. And we need to be able to control them window by window. So unfortunately, we had to start from scratch. We had to put a lamp and a bulb in each of our 182 windows. And they were all delivered to right here at the RI. And we can see here 182 boxes, 182 lamps being delivered. It took everybody to try and get all of these boxes and start unpacking all of our just simple lamps here. But now we need 182 light bulbs. So let's go back to Swan's incandescent light bulb. Could we use these? Now, the great thing about Swan's light bulb is it's really easy to see how these work. If we just take our first bulb here, we can see just our normal tungsten filament inside, and the metal is tungsten because it has a very high melting point, and that's important. So when I plug this bulb in, what we see is the current has been passed through the metal in our light bulb, and that heats up the metal, which makes it glow. Now, the glass is actually quite important for our light bulbs here, but don't just take my word for it. If we remove our glass, like we've done in our second bulb here, what do you think is going to happen? Is this going to work? We've removed the glass. So it's exactly the same as this one. A few shaking of the heads. Anyone nodding the head? Oh, a few nods of the head as well. Okay, well, let's plug it in and find out. So I'm just going to put some little safety specs on here. Right, are we ready for this? You see it? So it did glow, but then very quickly it burnt out. And the reason it does that is the glass is protecting the filament because there's protective gas around that filament. So it's not allowing the air to get to that filament. So once the oxygen gets to there, it burns out very, very quickly, as we just saw. But can we keep it glowing in another way? Well, Andy's going to help me with this, and I'm going to put my specs back on. Hi, Andy.
Hi.
So what we have is another bulb which has had the glass removed. So it still has our filament in there, but the glass has been removed again. And what Andy's going to do is fill this container with liquid nitrogen. Liquid nitrogen always looks really good, doesn't it? Right, so if I now dip my light bulb in the liquid nitrogen, so it's completely covered, and then I turn it on, is this going to work? Yeah? Let's see. It works. And not only does it light up, but it stays lit up as well. And the reason for that is the liquid nitrogen is pushing the oxygen away from that filament. So the oxygen is not surrounding our tungsten metal anymore, so it allows it to keep glowing. Great, thanks very much, Andy. Now, the problem with Swan's light bulbs are they lose a lot of electric energy as heat. And we need not one light bulb, we need 182 light bulbs. So we needed something much more efficient. So we decided to look at LED bulbs. Now, they're still quite expensive, but they're much better at converting electrical energy to light energy. So they use much less power and they don't get as hot. So that's what we did. We got 182 LED bulbs, one for every window. Now, we needed to make sure that we could actually see that window glow. So we used some baking paper here to diffuse the light in our windows. Then we needed to make sure the light was directed away from the room and out of the window, so out so we could see it from outside. So you can see here, we've used some reflective film on our windows as well. So step one, part one, done. We've managed to make every window a pixel just by using desk lamps and LEDs that we've bought at the local DIY store. But there's still a big difference between lights and windows in making a screen, isn't there? If you think back to our small screen here, we have lots of LEDs, but we also need ways of controlling all of those lights. So how do we tell each lamp what to do? Well, it's easy just to wire a bunch of LEDs on the ground. We could do that. But it would be really, really difficult to scale that up to what we need for our giant skyscraper here. Now, I know what you're thinking. Well, there are already wires in the building, aren't there? Surely everyone's got a network cable these days. And the answer is yes. this has a network cable, just the same as the things that you guys will have at home as well, just an Ethernet cable. So we could network all of our windows of lights just using network cables, couldn't we? Well, before we answer that question, I want to show you something really, really cool with network cables right here tonight. So if anyone's seen the Matrix film, you know that part in the Matrix where the two actors freeze in time and they're suspended in the air, so they jump up in the air and they're frozen in time and the cameras pan around them? You know that? You've seen that before, yeah? Well, let's try and recreate that here. What we have here is a semicircle of 40 Raspberry Pis. Now, Raspberry Pis are just little embedded computers, and I'm sure many of you have used these before. If we have a look in a bit more detail here, we can see that it has a little LCD display on the top, it has a camera, and it also has our Ethernet cables, so it's a wired network. So we can use all of these cameras to take a photograph at exactly the same time and then stitch all of that information together. So our computer down here, Andrew, is going to be able to we're going to take the photographs at exactly the same time. So Andrew's going to trigger that information, okay? Now, we're obviously missing a couple of things here. Volunteers to be jumpers. Okay, let's go. You there, please? Yes? And you here. Okay, great. Thank you very much. All right. What's your name?
Ed.
Ed. Okay, Ed. I'd like you to stand probably about here and then just face that fire exit sign a little bit there. Okay? Come in a little bit further, I think. Just need to get you about right. Okay, what's your name?
Harriet.
Harriet, okay. Right, Harry, if you just turn to where you were sitting and then just go backwards here and then just face that exit sign there. Right, we should be good there. Right, now hopefully you guys are good jumpers. Yeah? Yeah. You've volunteered now, Harriet, so you have to be a good jumper, okay? Yeah. Now what I want to see is the craziest jump you've ever done. So I want to see arms up, I want to see legs up, okay? And I want to see you getting nice and high as well, okay? Are we ready? 3, 2, 1, jump! That looked pretty good to me. Thank you very much. Just stay there. Harriet. Wow. That was brilliant. Now, Andy, did we get it? Yeah? Okay. Right. Let's turn around and see how it looked, because it looked pretty good from where I was. So let's see if we managed to capture that. That's brilliant. Look at that. Excellent. I like the big happy faces as you're doing it as well. That looks amazing. And we've done that with really simple electronics. You look fantastic. Well done, both of you. Brilliant. Thank you. And that's a great way to show a wired network and what it can do. But unfortunately, we can't plug our lamps straight into a network point like we could with our little embedded computers. So we still need to find a way of turning our desk lamps on and off if we're going to be able to play this game at the Shell Centre in about 30 minutes. So I need to replicate something. If I was turning a lamp on and off, I need to replicate what my thumb would be doing, turning that lamp on and off. And I need something that is telling my thumb what to do. So I need a bit of a brain, and I need a mechanical thumb. So what we have here is another little thing that you can do at home. And what we've got is a tiny little motor, and you can hack this from something else in your home. And we're going to use that to switch the light on and off. So you can see it's just attached to the switch on the lamp. And the good thing about this is there's no mains tampering, so I haven't had to tamper with the electric mains, so it's really safe for you to do at home. Now, this motor is attached to another little circuit board here. And again, they're probably little boards that you've already played with before. They're not expensive, and we've just got some software from the internet as well. The difference with this is it has a wireless receiver on board. So we should be able to communicate with our motor wirelessly. But I'm not going to do it. I'm going to get somebody else to do it. And I'm going to go up here again. I'm not going to choose the same person, Sasha, don't worry. I'll choose you instead. Okay, what I want you to do, what's your name?
Sam.
Sam, okay, Sam. What I'd like you to do is to wirelessly turn my lamp on and off. Now there might be a little bit of a delay because we're using the Wi-Fi network here, okay? But just using the on-off switch there, you should be able to turn it on first, so let's try. Have a little bit of a delay. Brilliant, excellent, so turn it off. Excellent, so all the motor is doing is just rotating. Try it again just to make sure it works. Excellent, and we'll turn it off. Just make sure you can turn it off. Do you turn the lights off at home?
Yes.
You do? Oh, you're very good. You're better than a lot of people I know. Very good. Thank you very much, Sam. Okay, so what was happening there was Sam was using the Wi-Fi signal, which turned the motor on and off, which allowed the switch to then switch the light on and off. And this is something that you can try at home. Now, I've mentioned something there that we haven't really talked about yet, which is Wi-Fi, or a wireless signal. And this is going to be crucial to making our Skyscaper game work. Now, our switches will rely on Wi-Fi signals to turn them on and off. So wireless would be a much better solution for our network because of the scale of our challenge. So instead of using our wired network now, our Ethernet cables, we can use a wireless network. And wireless networks are everywhere now. We've actually become a little bit too good at using wireless networks. If you think about the wireless devices just you guys have in your home, I bet every single person in your household has got a smartphone, maybe a tablet, maybe a laptop. You'll have a wireless router in your home, and that's just in people's homes. So we need to look for different ways, for new ways to be able to send information wirelessly. And perhaps our humble light bulb will give us the answer. Could we use visible light to send information wirelessly? Now that sounds crazy, doesn't it? How can we use light to send information wirelessly? But I've got a really, really good demo to show you here. And I'm going to need a volunteer to help me with this. Now I probably haven't chosen anyone from the centre yet as well. So I'll choose you with the grey jumper on. Yep. Okay. Okay, what's your name?
Roisin.
Roisin. Okay, Roisin, if you want to come and stand over here. I really like your necklace as well. Good light bulb. Okay, what we have, Roisin, is 2 laptops and a torch. And what we have is this laptop is running a movie. What I'd like you to do is to be able to carry the information that's on this laptop, which is just playing a little movie, and send it wirelessly to that laptop. And all you need to do is turn that torch so it faces the laptop over there. So you can just place it down, you don't need to hold it. Yep. There is a movie playing over here, and the same movie is playing on that laptop as well. Now just to prove that this works, just angle that torch away again. So it's just out of the way of the system. Now, that one stopped, but let's just check this one is still working. Come around here. So yeah, the video is still playing here, but it's stopped over there. So we've stopped the movie by just removing the light. Now shine it back again just to make sure we've got it. And then the movie should start playing again, and it's starting to play. All we're doing is using this torch. Now inside this torch, there are lots of LEDs and they're flashing millions of times a second. So it's like the old Morse code. Now in the future, we might be able to send information over the internet to laptops, just like Roisin's been doing there. And this would free up the space in the Wi-Fi networks and prevent a lot of further interference. But thank you, Roisin, for your help. Now, sadly, Li-Fi was a little bit too advanced for our Tetris game. Because if we shone lots of lights like Roisin had there, we wouldn't see our own Tetris-style game lights. So we could fit servo switches to every lamp and send a Wi-Fi signal instead of a Li-Fi signal. But our router only works over a very small distance, and our building is actually pretty big. So we need something bigger, something stadium-sized. So is everyone wearing their wristbands? Yeah, everyone hold them up in front of their face like this. I feel very left out because I don't have one. Right, can we dim the lights, please? And can we activate the wristbands? Wow, that looks amazing. Oh, I don't feel so left out because the parents and teachers don't have them either. But it looks pretty good, doesn't it? Looks fantastic. Right, these are called Xylo bands. And to help us explain how Xylo bands work, please welcome Jim Regler. Hi, Jim. Hi. They look brilliant. Now, these look absolutely fantastic, Jim.
This one is for you.
Yay, brilliant.
And this is a wristband that has LEDs all around the strap and a small radio receiver here,
Yeah, okay.
which we can control using this remote control.
Right, okay.
And if you would like to press some buttons on the
have a
remote control,
go,
so if you
yeah.
press this button here, they will turn green.
Well,
And if you press this button here, they go red.
fantastic.
And if we press the glow button at the top, they will all start to glow nicely.
This looks brilliant, by the way. Fantastic from down here. Okay, now I know you can actually group these as well.
Yes.
So how do the wristbands know which group they're in?
What we can do with the wristbands, we can tell them which group they're in by zone, and I can demonstrate the zoning by pressing this button here.
Excellent.
And they obviously respond when they are told to by zone.
That's fantastic. Now, as you know, Jim, we're trying to build a giant games console on a skyscraper this evening. So we need our Wi-Fi signal to go quite long distances. So how far have you actually got in terms of distance here?
Well, we've built this system, obviously, to run stadiums and concerts. So we have successfully covered distances up to 500 metres and beyond.
Brilliant, that's really good. And I think actually we've got some footage here of showing a Coldplay concert. And wow, look at all of those. That looks awesome.
Indeed.
And how many were there?
There's about 30,000 there.
30,000. That must have been an amazing moment just to see that invention come to
Absolutely
life.
fantastic.
Thank you so much, Jim. I don't feel as left out now. I have one now, that's good. And it looked brilliant, absolutely fantastic, even just 300 of us. So imagine what it looked like with 30,000 of them. Now, we considered using these wristbands because they've got LEDs as their lights. We can control them wirelessly from a central point. We can even control them individually or in groups. And they're cheap to produce. So this all sounds fantastic. But the problem with these is the lights just aren't bright enough for us. So we need something that's really, really similar technology that we've all got here, but something a little bit brighter. So we had another trip to the DIY store, and we bought some LED bulbs. But these bulbs are just a little bit different. Now what we have is this bulb, but we've exploded it out here just to show you what's inside it. Now, there is some glass around this bulb, but it's actually just used to diffuse the light, so there's no gas in it like the incandescent light bulb needs. What you'll notice about this is what you might not expect in a light bulb is this part. This is the radio receiver, so it's just like the ones that we all have in our wristbands here. And this has a Wi-Fi network on it. So the Wi-Fi network will send information about the bulb's brightness, and we could even change the color of these bulbs as well. And because it has a radio receiver, we can do it all wirelessly, so we could just do it from a mobile phone app. So these seem perfect. So we've got 182 bulbs that we can wirelessly control. So we can put them in our lamps in our building and control them wirelessly in the windows. It would make the windows different colors, so anything we want just in an instant. And we can send a wireless message that would pass that message to the next bulb, which would pass it to the next bulb, which would pass it to the next. And that's called a mesh network. And it would make sure that no bulb is actually forgotten. So, hardware done. I'm getting more confident on this, actually. I'm getting up to where you were at the beginning. So we've done the hardware, but we need step 2. We need to control the software. So we need to write some programming. So let's do some coding. Now, I'm aware these are the Christmas lectures, and we haven't blown anything up yet, have we? Seems wrong. So please welcome CBBC resident explosives expert, Fran Scott. Hi, nice to see you. Nice to see you. Okay, now I understand we're going to have a selection of balloons.
We are.
Here. And of course we have to have some hardware as well to be able to use our software on.
Slowly coming on.
Slowly, yes. Okay, so if you just talk us through what's happening
So
here.
basically, these aren't just ordinary balloons. These balloons are explosive balloons.
Excellent.
They're full of a highly flammable gas, so when we let them off, they won't just pop. They're going to be small fireballs.
Ooh, that sounds good. Okay.
And what we're going to do is we're going to code those fireballs. Because all that coding does is it's a way to tell a computer how to take an input and convert that into some kind of output.
Right, okay. So how do you start writing code like that, Fran?
Right. Well, the thing is, to start with, you need input. Mm-hmm. So inputs usually, for an explosion, are a big red button.
Yep.
Here, we've got our small blue button.
We like to be different.
We
That's
do.
Good, good.
So that's going to be our input, but we need to code our input. So if we just look up at the screen now, that is our code that we're going to use to tell a computer what to do.
Okay, brilliant.
And it's in Python, which is a programming language. And if we just look here at that white text, it says that the blue button is allocated a number. Mm-hmm. And that number refers to digital switches within inside our small computer, because this is what we're going to use to set the explosions off.
Okay, right.
Different numbers mean different switches.
Right, yep, got it.
So blue button, number 22. And all we need to do is go down to this part of the code where it says input chosen. We delete the words input chosen, and we need to put in our number. 22.
Okay. Yep.
Simple.
That's good. Okay. Right. And I see we've got an input, so that's good.
Yeah.
But now we need outputs, and I'm guessing the balloons are the outputs?
They are. You can have an output
Cool.
that's a screen, or you can have an output that's exploding balloons.
Right. Excellent.
I've gone for exploding balloons.
We like it. Good.
And these are programmed to go off 1 second after each other.
Okay. So we need to order which way those balloons are going to go off.
Exactly. We haven't programmed that bit yet.
Okay, so I think these guys should...
I think they
choose
should.
that. Right, okay. So we need to choose which colour balloon goes off first. Okay, so we've got yellow, blue, green. So have a think about which one you want to go off first. If you want the yellow one to go off, shout yes now. Yes! Blue? Yes! Green? Yes! Oh, green.
Green.
Okay, green.
Green.
Definitely green.
All I need to do is look at the number that green's allocated, which is 13.
Okay.
And I put that here where it says balloon 1. I just need to put in number 13 there.
Right.
And that switches that output on. But then, just like your switch before, I need to switch it off again. So,
Sounds good.
here, I put 13 again.
Right.
But that's the first balloon.
So we need the second one now?
We do.
Right. Okay, so we've got yellow and blue left. Okay? If we want yellow to go off second, shout yes. Now? Yes! Blue? Yes! Oh, definitely blue.
Blue, so number 12, I'll get
yellow.
coding that.
I don't know what's wrong with yellow.
Number 12 there. And then yellow is 13. So we put, no, yellow is 11.
11.
So we put 11 there, and then 11 in this one.
Right.
Here.
Brilliant. Now, I also saw something before, yeah, that's still up there. Now it says output 16, print boom. That
Yes.
sounds really good to me. What's that?
Well, that's because these balloons, they're like our countdown to our final explosion, and that's why they go off 1 second after each other.
Okay.
But what we now need is our final explosion.
Okay.
So put those on.
Right. Brilliant.
And that final explosion comes from in here. And what we've got is inside here, we have got a balloon. And that balloon is full of an explosive mix of gas. So not just highly flammable gas, an explosive mix.
Okay.
So it's going to be loud.
Yeah,
And I'm
excellent.
just going to put that inside there. And inside the oil drum, it's going to be a little louder.
Right.
But I've got some things to just put on top of the oil drum so we can see the explosion.
Great. Okay.
Just
Oh,
here.
plastic balls. Brilliant. Get ready to catch them, everybody.
Thank
Okay.
you.
Oh, that's all right. Okay, so we've got our balls.
Yep.
What else do we need to do?
We just need to run our program for me to do my safety checks.
Okay, so
and it's going to be loud.
And I need all of you guys to put your hands over your ears. It's going to be very, very loud. And can we lower the lights, please?
Here we go.
Thank you. I'm going to stand over here.
Fingers crossed.
Here we go.
So,
5, 4, 3, 2, 1, fire! That was amazing, Fran. Okay, thank you so
Thank
much,
you.
Fran. Now, if anyone tells you that writing code is boring, you need to show them that clip of Fran doing those explosive things. That looked absolutely brilliant. And what Fran was doing there was just writing code for a simple set of events. And that's exactly the same as we need to do for our game. And here's the code for our game. Now, our game is quite long. I'll not go into every single detail for you here, but we could just take a snippet of that. So we could just look, for example, at how we just clear the board and start at the top of our screen. Then we could just say, well, okay, let's just look at how we actually play, or when it gets to the bottom, how the code tells the building that it's game over. Now, this looks like a long, long piece of code, but it has to be, because we're dealing with lots of different possible controls here. But we're doing exactly the same thing as Fran did with her code. We're taking things step by step, and we're thinking in a very methodical and a very ordered way. So we've written our code. We've got our code now. The final thing we need to do is build an input device, something to actually control our game. So, Harrison, are we at the Shell Centre yet? Can we go live to the South Bank, or are we a bit too early? Oh, brilliant. Okay, excellent. Hopefully it's not too cold. Okay.
It's freezing.
Now, we are coming back to you, Harrison. We're almost there, so just bear with us, okay? Okay. Right. So, our controller doesn't really need to be anything complex. And we should be able to make anything control, well, anything. For example, I should be able to make these jellies control my keyboard. Let's just see. Sounds crazy what I'm saying, doesn't it? Let's just see if that's true. If I just attach myself to this circuit, I should be able to play my jellies. I can make a piano with jellies. Fantastic. And what's happening there is I'm just using a very simple circuit board here called a makey-makey circuit board, which is turning each of my jellies into a piano key. So that when I connect myself to this circuit, I'm completing that circuit by pressing one of the jellies. So I'm becoming part of that circuit. And the computer doesn't realize it's a jelly. It just thinks it's a message that's coming from its keyboard or its mouse. So I should just be able to play a tune. Or I'm a bit wobbly. Now, could we replace our jelly? Could we scale this up and replace our jelly with people, for example? Well, let's see if we can do that. Let's see if we can turn this front row here into a keyboard. So what I want you to do is just stick your hand out like a high five, and let's see if this works. So I'm going to connect myself to this circuit. Should we try and play a tune? Ready? What do we think? Sounds pretty good. I think we could make that work for our skyscraper. I think we could make a simple gamepad, control pad, just using our simple circuit board. Now, we probably wouldn't use jelly. We could just use some special modeling clay that just sets here and just forms into a bit of a flexible plastic. So it's really good for making and fixing things. So we've just attached a blob on each of our clips here. So step 3 complete. We have our controller. So we have a gamepad. We are ready to play. Now, let's just recap here. We've turned our building into a screen. We've managed to control all of those lights. We've managed to code that game, so we've done some software as well. And we've just made a gamepad. So I think we're ready. What do we think? Let's go live to the South Bank, please. Okay, great. So the shell building is now in darkness, so that's good. Ready for our lights. Okay. And is Harrison there? There he is. Great. Okay. Now, do you have a gamepad, Harrison?
Yeah, I've got it here. Yeah.
Excellent. Now, I know it looks funny, but I assure you it works. Okay, we're all set. Is everybody ready for this? Because this is it. I have no idea if this is going to work or not. But there's only one way to find out. Can we turn all of the lights red, please? Fantastic, yes. We're controlling it. Can we turn them green? Brilliant. Excellent. And blue? Fantastic. I can't believe it. This is brilliant. Okay, Harrison, are you ready to play the game?
Yeah.
Okay, now I think we should do a countdown for him from 5. 5, 4, 3, 2, 1. Let's play. Fantastic, he's already playing. That's brilliant. Okay, now he's moving his first blocks. I can see a T shape just down at the bottom there. And he's moved it to the bottom, so he's got his second one at the top there now. And that's moving down. Now, I think we deserve to give the technical team that made that happen a huge round of applause. Brilliant. And we've got 1 or 2 pixels out there, just like you maybe have with an old screen or something. But it looks brilliant. We've just turned a London skyscraper into a games console, and it's working as it should. Harrison's pressing a button, and it's forming a circuit. The signal is then going into the laptop, which receives that instruction from the gamepad, and is adjusting that position of the falling block. And it's also converting our screen of that pattern of our 13 by 14 pixels. And when we put all of this together, it means Harrison can stand in Jubilee Gardens and play Tetris-style game on a skyscraper. I hope by following our journey from crazy idea to working solution, you've had a glimpse into the mind of an engineer. You've seen how the tools around you can do amazing things. You've seen how to think about things in your home slightly differently, and how they can be hacked to help you realize your own crazy ideas. You've seen how we can troubleshoot problems when they arise, and how often the best solution is actually the simplest one. And perhaps just because it's fun, is the best reason to do anything. In the next lecture, we're going to be looking at the telephone, Alexander Graham Bell's very own light bulb moment that brought us all much closer together. And we'll be attempting to use all of our senses to communicate and beam a special guest into the theatre by hologram. Okay, Harrison, have you had a good time playing Tetris on our skyscraper?
Yeah, definitely. I'll never get a chance to play on screen like this again.
Good. I'm glad. Even though I know you look really, really cold, you did a fantastic job. Thank you so much, Harrison. And thank you to everybody here as well. Good night.